Welcome to emstatonline. Today we are going to see central limit theorem. Let us consider the sequence of random variable x1, x2, x3, etc. are random sequence. The concept of convergence of random sequence is essential in the study of random signals. The convergence everywhere and almost everywhere. If f1 of x and f of x are the distribution function of xn and x respectively, such that f1 of x tends to f of x as n tends to infinity for every point of continuity of f of x, then the sequence xn is said to be converged to x in distribution. It's closely associated to the concept of convergence in distribution is known as central limit theorem. Central limit theorem, two forms. First one is Leibniz forms, another one is Lindbergh-Levy forms. The Leibniz forms, the sequence of random variable with e of xi equal to mu I and variance of xi equal to sigma I squared. And if Sn is equal to x1, x2 plus etc. plus xn, then under certain general condition, Sn follows a normal distribution. The main thing be a sequence of independent random variable. Under certain general condition, Sn follows a normal distribution with mu summation of I is equal to 1 to n mu I and variance sigma squared equal to summation of I is equal to 1 to I sigma I squared as n tends to infinity. When n tends to infinity, the distribution tends to normal distribution by central limit theorem says. That is, n is very large. By central limit theorem, given distribution tends to normal distribution. Then Lindbergh-Levy forms, if x1, x2, etc. xn be a sequence of independent identically distributed random variable with e of xi mu, variance of xi sigma squared, where I is equal to 1 to etc. and xn, x1 plus x2 plus etc. to xn, then under certain general condition, Sn follows a normal distribution with mean n mu and variance n sigma squared as n tends to infinity. So what is the difference between Leibniz forms and Lindbergh-Levy forms? In Leibniz forms, a sequence of independent random variable. Lindbergh-Levy is a sequence of independent identically distributed random variable. Here, if xn equal to 1 by n into x1 plus x2 plus etc plus xn. Then E of x bar is equal to mu and variance of x bar is equal to 1 by n squared into n sigma squared. That is equal to sigma squared by n. Therefore, x bar follows normal distribution n of mu comma sigma by square root of n as n tends to infinity. This is a corollary of this Lindbergh-Levy forms. So only distribution is independent random variable sequence in Leibniz forms and independent identically distributed random variable in Lindbergh-Levy forms. Example, a coin is tossed 10 times. What is the probability of getting 3 or 4 or 5 heads? Use central limit theorem. Use central limit theorem. But in this case, a coin is tossed 10 times. So n is equal to 10. What is the probability of getting 3 or 4 or 5 heads? Let P be the probability of getting, let P be the probability getting head in a trial. Therefore, P is equal to 1 by 2 and Q is equal to also 1 by 2. So 1 minus P. N is 10 times tossed. So we know that, so binomial distribution here, mean equal to NP, variance equal to NPQ. So here mean is equal to, n is equal to 10 into 1 by 2, that is 5. Variance equal to 10 into 1 by 2 into 1 by 2. So 2.5. So here mu equal to 5 because mean NP, we can use mu equal to 5 and variance sigma squared. So sigma is equal to square root of 2.5. To approximate the discrete probability distribution, to continuous probability distribution, probability distribution, add 0.5 to the upper bound and subtract 0.5 in the lower bound from the lower bound. That is 5 plus 0.5 and 3 minus 0.5. So the given distribution is discrete distribution. We convert, it's a continuous distribution. So P of 2.5 less than x less than 5.5. But the given problem is discrete distribution 3 or 4 or 5. Now the same distribution convert a continuous distribution. So that is equal to P of 2.5 minus mu by sigma less than or equal to Z, which is less than or equal to 5.5 minus mu by sigma. That is equal to P of 2.5 minus mu is 5, then sigma is square root of 2 is 1.58 less than Z 5.5 minus 5 by 1.58. So is a calculator, you get P of 2.5 minus, that is minus 1.58 less than Z less than 0.32. The normal distribution, we can write probability of 0 less than Z less than 1.58, the normal distribution, plus probability of 0 less than Z less than 0.32. From the table 0.4429, Z lies between 0 to 1.58 plus Z lies between 0 to 0.38 is 0.1255. So this value is 0.5684. So the probability of getting 3 or 4 or 5 heads is 0.5684. If x1 x2 etc. xn are Poisson variable with parameter lambda equal to 2, use the central limit theorem to estimate probability of 120 less than or equal to Sn less than or equal to 160, where Sn equal to x1 plus etc plus xn when n is equal to 75. This is example number 2. Solution: Sn is equal to x1 plus x2 plus etc plus xn and n is equal to 75. So parameter given, parameter is lambda equal to 2, therefore mu equal to 2. So let Z equal to, already we know that Sn minus n mu by sigma into square root of n. So n is equal to 75, n mu that is equal to 75 into 2, that is 150. N mu is 150 and variance is 2, so sigma is equal to square root of 2. Why? In Poisson distribution, mean equal to variance. Mean is equal to variance. So P of 120 less than or equal to Sn less than or equal to 160, that is equal to P of 120 minus n mu divided by sigma into square root of n less than or equal to Sn minus n mu divided by sigma square root of n 160 n mu divided by sigma square root of n, that is equal to probability of 120 minus 150 by sigma into square root of n. Sigma is square root of 2 and n is 75 and square root of 150 less than or equal to Z less than or equal to 160 minus 150 divided by square root of 150. So 120 minus 150 divided by square root of 150, use the calculator, 2.45 less than or equal to Z less than or equal to 0.82. So this one we can write minus 4 pi less than or equal to Z less than or equal to 0 plus probability of 0 less than or equal to Z less than or equal to 0.82. But it's a normal distribution, we can write 0 less than or equal to Z less than or equal to 0. That is 2.45 plus probability of 0 less than or equal to Z less than or equal to 0.82. From the table, this value is 0.4929 plus 0.2939, that is equal to 0.7868. So probability of Sn lies between 120 to 160, 0.7868. Now example 3. Let x1, x2, etc. x100 be independent, identically distributed random variable with mu equal to 2 and sigma squared equal to 1 by 4. Variance is given, mean given. Find P of 192 less than x1 plus x2 plus etc. plus x100 less than or equal to 210. But previous problems, they asked use central limit theorem. But in this problem, indirectly given independent identical distribution, Lindbergh-Levy forms. So here, solution. Let Sn equal to x1 plus x2 plus etc. plus x100. So n is equal to 100. Mu given to sigma squared equal to 1 by 4, so sigma equal to 1 by 2. And Z equal to Sn minus n mu by sigma into square root of n. So probability of 192 less than x1 plus etc. plus x100 less than 210, that is equal to probability of 192 less than or equal to Sn less than 210, less than 210. That is equal to P of 192 minus n mu by sigma into square root of n less than Z less than 210 minus n mu by sigma into square root of n. So that is equal to probability of 192 minus n mu. So 100 into 2, so 200 sigma into square root of n, 1 divided by 2 the square root of n, 1 divided by 2 into square root of 100, square root of 100, that is 10, less than is less than 210 minus 200 by 1 by 2 into 10. That is equal to probability of minus 1.6 less than is less than 2. So we can write probability of minus 1.6 less than z less than 0 plus probability of 0 less than z less than 2. So normal distribution, so 0 less than z less than 1.6 plus probability of 0 less than z less than 2. So from the table value, that is 0.4452 plus 0.4772. That is equal to 0.9224. So x1, x2, x3 up to x100 are independent and identical distribution random variable. We can find (192) less than z, n less than 210. That is 0.9224. The resistors R1, R2, R3 and R4 are independent. Random variable and is uniform interval and is uniform in the interval 450, 550. Using the central limit theorem, use central limit theorem, find one and 00 less than or equal to R1 plus R2 plus R3 plus R4 less than or equal to 2100. Find probability of this one. Solution. Here the random variable x, is said to have uniform distribution. Random variable x is said to have uniform distribution. On the interval, suppose general interval a comma b, if the probability density function is f of x equal to 1 by b minus a, where a is less than x less than b, otherwise 0 elsewhere. So 1 by b minus a, already we know that mean of uniform distribution a plus b by 2 and variance b minus a the whole squared by 12. So here a is equal to 450, b is equal to 500. So mean 450 plus 500 by 2, that value is 500. And variance b minus a 5, b is equal to 550, b is equal to 550. So 550 minus 450 the whole squared by 12, that is equal to 833. Use calculator, we can find. So mu is equal to 500 and sigma squared is equal to 833.33. So sigma equal to square root of this one. And given 4 resistor, so n is equal to 4. So n is equal to 4 since Sn equal to R1 plus R2 plus R3 plus R4. So probability of 1900 less than or equal to Z less than or equal to 2100. That is equal to probability of 1900 minus n mu by sigma into square root of n less than or equal to Z 2100 minus n mu by sigma square root of n. So that is equal to probability of 1900 minus n mu 4 into 500, sigma means square root of 833.33 into 2 less than or equal to less than or equal to 2100 minus 4 into 500 divided by square root of 3.33 into 2. So use calculator. P of minus 1.73 less than or equal to Z less than or equal to 1.73. So in normal distribution, minus 1.73 less than or equal to Z less than or equal to 0 plus probability of 0 less than or equal to Z less than or equal to 1.73. This one we can write 0 less than or equal to Z less than or equal to 1.73 because normal distribution. So 0 less than or equal to Z less than or equal to 1.73. We can write 2 into this value. Two into P of 0 less than or equal to Z less than or equal to 1.73. From the table, this value is equal to 0.4582, that is equal to 0.9164. So the 4 resistance in between 1900 to 2100, the value is 0.9164. So in central limit theorems, the random variables are independent, then we can use Leibniz forms. The random variables are independent, identically distributed, then we can use Lindbergh-Levy forms.